Okay. Okay. So, I want to. I'm just going to say the picture we want to aim for, and we'll work towards it. To it today. It's a little bit of geography. So this geography map, where like we define certain structures, and then we try to like figure out kind of where they are, like relative to each other. And so, so we defined a few different types of rings. Okay, these are just arithmetic systems, numbers, sets of numbers, if you want. So we defined this notion of the Euclidean domain. And let's make like a Venn diagram. And then we also define this notion of principal ideal domain. I don't know, did I state it or did I prove it? The Euclidean domain is going to be a principal ideal. And within that, of course, these guys are in a larger world where we have all integral domains, no zero divisors. But there's something in between, and we saw that just at the end last time. We saw, if you recall last time, we started out reviewing integers and how we could factorize integers and how we had things like the fundamental theorem of arithmetic that helped us to know that this factorization is unique and the notions of primes and irreducibles were sort of the same thing. And then I gave an example right at the end of the class last time where we saw that something weird happened in this particular ring. It was like z times square root of 5. So we got some kind of non-unique factorization since irreducibles. So the thing in between, where the fundamental theorem of arithmetic works, we also have a name for, which I'll introduce today. And this is a unique factorization domain. And so, in fact, every PID, and this is kind of the main thing we want to show today, every PID is a unique factorization domain. So if it's a principal ideal domain, we can do what we want in terms of fundamental theorem of arithmetic. Nice factorization. Now this is a very deceptive picture, because if I were to sort of draw it to scale, whatever that means, this integral domain bubble would be huge. Like, okay, I mean, so compared to, mean, the UFD bubble would also be very large, much larger than the PID and the ED in the Euclidean domain bubble. But if you go to the UFD bubble, you can extend. I guess I'll say some things. Maybe I don't know if it not makes sense or what. These two worlds are sort of like a one-dimensional world. You want to think dimensional. There's a notion of dimension of a ring, and these guys are sort of exclusively one-dimensional, zero dimensional. UFDs, they can be any dimension. So in some sense, you get a bunch more examples. Much richer world. Integral domains are like all spaces, like kind of that don't break up into little subsets. There's kind of integral domains are enormous compared to this. So it's not really. I'm saying is that this is, don't take the size of these things too seriously. But this is what we want to understand. Questions? The main result is, again, that we have this PID as a UFD, but I'll say a little more in a second. So I just said it a second ago, but I don't remember. Did I prove it? That a Euclidean domain, I mean, I don't need to prove it. I'm just going to kind of say it again. That the proof is sort of, we've done it in a sense in several different cases. Is well, so who here, if they were like given, an exam right now, like would prove this fact? I'll raise your hand. Okay, so nobody. All right, that's good to know. So like let's like work through mentally how to prove this. So what do we need to show? We want to show something that's a principal ideal domain. Definition. We have an R here. The domain. I want to show that it's a PID. I need to show an ideal R, and I is what? Principal. The principal ideal domain. All ideals are principal. That's what it means. And which means I have to find an element in R that generates this ideal. So this is the principal ideal associated to a particular element in R. Okay. All right. So that's what you want to show. Want to show, we need to show. All right. So how do you show it? Well, you do, I think I said this verbally, but let me just repeat it again. You do what you did for integers and for polynomials. Same thing in both cases when we're talking about subgroups of integers, of the additive group of integers, and ideals of polynomials. We did basically the same thing, but now you do it for this Euclidean domain R. You choose A in your ideal so that, remember, Euclidean domains, we have a size function. Size of A is smallest. Of all the elements of I, you can take the size of each element, you get a list of natural numbers. That's a natural number, so that's the smallest one. Choose some A that's sent to that smallest one. Okay. Now then you claim, I said I wasn't proof it. I equals A. And the proof is the same as the proof we did in both cases. If B is in I, then divide by A. B equals A times Q plus R, with the size of R less than the size of A. Right? But B is in I, and A is in I. So B minus AQ, which is R, is in I. Right? And A was chosen so that the smallest size. So R must equal 0. And this is where this special size of 0 is like negative infinity or something. We don't include 0 when you're taking all the sizes. Except that means then that P is equal to AQ. Okay, so that means that all the elements of the ideal are multiples of A. It's an I. Okay, there's the proof. I mean, it's so familiar. We've done it 2 times, so this is the 3rd time, and the last. Question? If it's a logical pattern, right? We have this, we've developed, you see some basic techniques in math where you're proving something a certain way. You abstract some of the essentials of those basic techniques, and then you can prove it much more generally. Okay. The Euclidean domains are principal ideal domains, which means we do have this kind of part of our geography. But now we want to kind of extend this a bit and get this part. This D part, domain, is just obviously saying all of these are individual domains, the part of the definition. Okay. So in order to do that, we need a notion of greatest common divisor, and that's something we can do inside of any domain, any integral. Let's make a definition. We'll make a couple of definitions. One. So let A and B the elements of R, where R is an integral domain. So now this is a kind of interesting definite versus indefinite articles, right? A greatest common divisor B of A and B element R satisfying following 2 properties. Well, one, he divides A and B. Common divisors, so this should divide both of them. And okay, so we're in an integral domain. So greatest is the kind of operative question. What does it mean to be great? To be greatest. I mean, we all know you guys are all great, but what does it mean to be greatest in terms of like a measure? So you don't have, this is not a Euclidean domain. We don't have a size function. But what we do have is we want to say, we have a notion of sort of dividing. And so we can say, if anything else divides A and B, then it must also divide B. That sense is sort of. So if E divides A and B, then E divides D. Okay, so couple of things to note about this definition for the second notion of A. We don't make any claims of uniqueness here. It's not the greatest common divisor. It's a greatest common divisor. So if we're talking in this level of generality, and I say, what's a greatest common divisor of, I don't know, 24 and 16, it's fair for you to say, huh? What? 8? 8? Everyone says 8? Nobody wants to be different? -8. There, good, you're different. Always said that. I'm joking. No. Yeah, right. -8. -8 works in this context. I think most books in high school or something, or middle school or whatever, they'll say, that's a natural, it's a positive. But okay, once we're in this kind of level of generality, we don't have positive, negative. We haven't made that preference. So it's fair to say -8 is just as good as 8. It's not unique. All right, another definition I want is the definition of a UFD. So this will use both. So ring R D, which stands for unique factorization domain. If R is an integral domain, and every unit, so every A, let me say this. Every A in R, not equal to 0. I can so 0 has a unique factorization. Write it down. Equaling U1 and for PI irreducible. So I'm leaving open, yeah, the possibility that there are no PI, so that A is just a unit, and A is just so there's nothing here, in which case A is a unit. PI are irreducibles, and U is a unit. So you need to make some clarification here about uniqueness. What do I mean by unique? Well, of course, I can switch around the factors. I'm allowed to do that. But I can also replace one of the P's with an associate. And if you recall, an associate means you can multiply that by a unit. So I could take, like, for example, in integers, 6 is equal to 2 times 3, but irreducibles are, I could also write it this way. In other words, I can take a unit and kind of push it through however I want. Break up units however. So this is, uniqueness is up to that kind of ambiguity, but nothing else. So up to associates is what you would say. Yeah, that's right. The principal ideals are the things that are actually clear. Ish. Okay. Okay, so now I said a minute ago there are a couple of things about this. One was this A greatest common divisor. But the other thing about this definition 1 is that it's not at all necessarily true that given two elements of a given integral domain, there is a greatest common divisor. It may not exist in general. So there is a question as to whether or not such a thing exists. And happily, it does exist when R is a PID. So that's the next result we want. And it's very, again, it's a very familiar result. We've seen it in a couple of different contexts. But let's put it in this level of generality. Here's a proposition. So let's have R be a PID. And AB and R not both 0. Then any D, which D is an element of R, which D, the principal ideal generated by D is equal to the ideal generated by AB, is the greatest common divisor. E, following. So we have, well, maybe moreover, I'll say, but some of this is sort of from what I just said. Some of this is part of the definition. Okay, well, this is immediately from the definition. R times D equals RA plus RB. Definition of this ideal is the same as this ideal. B divides A and B. That follows from. Well, that's part of the definition. This is another property. If E divides A and B, then E divides and then this follows again immediately and easily, but it's property that there exists a new kind of thing, R and S in R, that D is equal to RA. Okay. This is very, very quick, so we can prove this quite easily. Let's do like a So certainly, if these are all true, then we get that D is the greatest common divisor, because these are the two properties that we need for D to be a greatest common. So let's assume that D is equal to this, and let's show that each of these holds. So if D is equal to this ideal, this is equal to, and this is the definition of this ideal. All things. And the ideal here is R times D. That's just definition. B, well, what do you guys think? Tell me. What should I do here? So R times, so I mean, maybe I should say, I said A holds, but the point is that I'm using this notation for principal ideal, which I think art is also the same as art, like the same, exact same thing. All multiples of A. Multiples of A by element. This is R. This on the left here is R. Sorry about the two notations. And I'm looking for B here. Well, let's just take one of these for a second. So maybe don't take A and B at once. Just take each of them individually. Okay. And maybe let's use what we just showed. So here we have this ideal. This is all things that look like something times A plus something times B. But there is something in there, right, that you can use, like 0. For example, I could take something times A plus 0 times B. If I took this to be 0 times B, in this big ideal, I have RA. What I'm saying is A is contained in RA plus RB. So is B, if I did the other, right? I took 0 times A plus all things times B. That's it. This is equal to D. Okay, moving on to C, right? Everyone's good? You remember last class? Forgot about that. What does it mean for something to divide it? It's an inclusion of principal ideals. So, got an inclusion of D inside of here and A inside of here. That inclusion indicates D divides both. All right, and then similarly, if E divides A and B, then A is contained in E. B is contained in E. So if two ideals are contained in another ideal, like a sum, that's contained in. Ideals are closed under addition. This is equal to D. And then D is just silly. I should really put circles around it. Way too many things it looks like. Sorry. Maybe there's a capital. I don't know. I'm sorry. This is like awful. Let me capitalize. Make sure I'm not confusing these with the actual. Capital D is obvious, right? Because you have this. D is in here. But D is going to be some multiple of A plus some multiple of B. D is an element. RD equals by definition RA plus RB. So it has to be some element, some multiple of A plus some. That's what this set consists of. So this is just like not hard stuff. The miracle of abstract algebra. Good question? No. I'll throw a brow here. It's okay. Not hard, but it's like kind of, I don't know, difficult in some ways to look at it. Like, I don't know, to process it. It's all about just, we've got these really super streamlined definitions now. And so sometimes people lose track of them. But if you can get used to using them, you will verify things much more quickly. Okay. So there's a corollary, part of the corollary that I want. I'm not going to do all of it, but let me do one part. So if R is a PID, then A and R is prime if and only if. Pretty simple. So in the proof of this, let me actually prove this in two parts. This is a corollary, but there's one part that we want to know in general, which is the following lemma. It says the following. A prime element of an integral domain is irreducible. So we have these two notions now, two competing notions for what our early understanding of prime number means. And what we're saying is, okay, well, there's an integral domain. If we have a prime element, then it will be an irreducible. Converse is not there, but it will hold. The corollary says it holds in PID. Let's see why this is true. So, any suggestions? Let's assume something's prime. So assume that P. We'll assume R is our integral. And what we want to show is we want to show that it's irreducible. Show that if it has a factorization into two elements, or that it does not have a factorization into two elements that are not units. Let's assume that P is prime and P is equal to A times B. We want to conclude that either A or B is unit, presuming P is non-zero and not unit.
Either A to B unit or B is
So why though? Why? Why are A or B? Well, I mean, that's a good question. So what does primeness mean? So we have two different notions now of what I think our familiar notion is, right? I think the more familiar notion is irreducibility, right? That's what you learn in elementary school. What you learn in elementary school is that If I have a number and I call it prime, it means that if it's factored into two things, one of them is one. One of them is one. I'll be factored into small. That's it. But that's not the notion of prime for rings. That's the notion of irreducible. So what the notion of prime for rings is that when you take the principal ideal of P, that it's a prime ideal, which means that if two elements, a product of two elements are in that ideal, then one of them is that. Or what it means is that if P divides a product, and P divides one of the factors. Again, let's look back over this last lecture. So what does prime mean? That it's not a unit, and if P divides a product, then it divides one of the two. That's the notion of prime. And your reaction is exactly right. It's frustrating. It's frustrating. Like there is a certain level of just like, what is the difference between these things that just seem exactly the same? A reasonable reaction. I don't know if that's what your reaction was for, but
Let's try to understand.
it's hard. It's hard because you're familiar with, there's a certain familiarity with this definition. If A is equal to a product of two things, then either one of these is one, is a unit, or like minus one if you do that. That's irreducible. But a prime, this is different. It's saying if it divides two things, then it divides one of them. Okay. So P is equal here, we're saying to A. P divide, that means the P divides the product. P divides itself. But P is prime. So that means that P divides A or B. Let's say A. You want to switch. Nope. Nope. 3, I mean, this is just true in general, right? So 3 will divide 9 times 5. The 3 doesn't divide 5. You could divide 4. In this case, it definitely only divides 1. So P divides A. So that means A is equal to P times some other thing. Let's say C. That's what it means to divide. Pretty definite. Now, what do you think we do? Anyone? Good. E equals P times C times B. Now we want to do all of the things that feel normal and natural. We are happily integral domain. So we can do at least one of the things that seems normal and natural. We can cancel. This is also equal to P times 1. We can cancel, and we get 1 equals CB. That means that C is the inverse, multiplicative inverse of B, and B is a unit. That's what we want. So primeness is a strong condition. Now let's just recall. 6 equals 2 times 3 equals 1 plus I times the square root of 5. 1 minus I times the square root of 5. And I squared root of 5. 2 divides. 2 is irreducible. 2 divides this product. You can easily show, not hard to show, it doesn't divide either of the factors. It's irreducible, but it's not prime. So in certain rings, these things are not the same thing. But in PIDs, they are. And that's what we're going to show. So we have that primeness will imply irreducibility, but do we have the other way? And that's what this corollary is. That's what this corollary is. So let's prove the corollary. Proof of the corollary. So now let's assume A is irreducible. And not call it A, let me call it X. Sorry, guys. Call it X or something. It's irreducible. And X divides AB. You want to show it's prime. You want to show it divides either A or B. So what do? Well, let's take the greatest common divisor of X and A. So that's D, the greatest common divisor, X and A. Well, D is a divisor of X, and X is irreducible. And that means that D is either a unit or X. Right? That's sort of the definition of irreducibility. You can't break it up anymore without it. So D, let's say because X is irreducible, and D divides X, we have either D associate of X, write it this way, this means it's an associate, the principal ideals are the same, or D is a unit. Well, if D is an associate of X because D divides A, that means X divides A. For this case, implies because D divides A, X divides A. And if you want, you can just think this is D equals X without the unit issue. But then you're done because you want to show that X divides AB implies X divides A or X divides B. If this is the case, D is a unit, then you have this last part of the last theorem that we had, proposition, namely, I have these integers, not integers, pardon me, these elements in my ring so that D is equal to this sum. That would be true in another case too, but here we get something. Then these are relatively prime, and I can write R times X plus S times A is equal to 1, or some R. Now it's true, it's equal to D, which is a unit. You can multiply that entire equation by the inverse, and you'll get 1. For some R and S. R and S. Now because you have 1, your identity on one side, you can multiply that whole thing by B. And AB is X. So the X times RB plus S. We get that X divides B. That's what we want. We want to say that either X divides A, which would happen in this case, or X divides B, which happens. So it's prime. So in PID land, these two different definitions are not different. They give the same elements. Irreducibles and primes are the same. Now, it's a very funny thing, and it's something I only really came to appreciate late in my math life. But this difference is actually really a very powerful difference in geometry as well. So rings where you have where you have this equality between irreducibles and primes, they only give certain types of spaces, and usually those spaces have a lot of symmetry. And they're not very interesting, actually. And spaces that don't have this, just sort of the vast majority of spaces in the world, this whole thing fails. So, kind of an interesting thing. If you do a lot of abstract math, keep that in mind. All right, so now we're going to use that for this PID implies UFD, and that's what we want to break down. This is a theorem. If R is a PID, then showing something is showing rings or UFDs is really nice. You can show something as UFD. It's a lot much easier. But as I said, it's okay. There's two parts to this. One part we've done most of the work for. We showed that primes and irreducibles are basically the same. But the other part we haven't done any work, which is to say we can get an irreducible factorization of an element. There's an existence and a uniqueness part of the UFD. So if I have an element that's not a unit or zero, that I can break it up as a product of irreducibles. That's possible. Finite product of irreducibles. The other part is to say that's unique. Uniqueness part we're basically almost done. We'll see. One thing. Existence is kind of a pain. It's not something I would expect you guys to just come up with. In fact, in some sense, the argument here comes from Emmy Noether, the very famous. I mean, she's not like the earliest woman mathematician at all by any means. There's some like earlier ones like Sophie Germain, people like way back hundreds of years. But for my like money, she's the greatest woman mathematician that's ever lived. She is late 1800s, early 1900s when she started, and came through Göttingen, which is like the center of the math world in Germany. Hitler did kind of came around and screwed up the German math. I mean, he expelled all the Jews, and like half of the mathematicians were Jews, and so they all came over here and like built the nuclear bomb. And so, like, not a good strategy in life. Learned later, but there's a lot of really interesting history there because he literally did. You know, he took Göttingen, which was like the capital of the world in math, this institute, Germany, and he like said this is only for pure German mathematicians. And so they like got rid of a whole bunch of mathematicians. Yeah.
So what you're saying is if world domination is the goal, we need mathematicians.
Well, certainly this was a big, I think this is like why people don't, this is another pitch, like for why pure math and pure science are really important is, yeah, you can make very bad decisions. There's like a high risk. You put a lot of money, like it's like Tesla or something, like you just like, you're never going to make profit until they make like a lot of profit. Like you have to like invest a lot and in these things that may seem very distant, but then when they come to fruition, it's very powerful. So anyway, Emmy Noether was in this group of mathematicians who left Germany and came to the United States, actually worked at Bryn Mawr for a long time. But she is really like one of the founders of modern algebra. I mean, definitely her and Hilbert, I think, are could be called like the founders. I mean, there are a lot of other great names, but her idea, which I'm now out of time to say it, was to sort of abstract a notion of finiteness by using this thing like an ascending chain condition. And said basically her condition is that if you have an ascending chain of ideals, that they have to stabilize at some point. In other words, if I have one ideal contained in another, and so on, at some point, those things have to just be equalities. It gives you a finiteness condition that allows you to control. Now, not all rings satisfy that. They're called Noetherian rings when they do. So PIDs are definitely Noetherian rings. And because of that, and because of them being PIDs, they have this irreducible factorization. So we'll talk about that next time. I think I'm going to have to change the schedule looking at how far behind I am. So I'll try to alter the homeworks a bit. Because I think we're just not going to get through what I wanted to get through this week. So don't get too eager with the homeworks unless you want to work ahead.
Yep.